All right. So, start off before I forget. So I have a meeting that's popped up today. So instead of 2 to 4, I'll be in my office from 2 to 3, and then I'll be there also from 4 to 5. All right. So that last hour just kind of gets shifting up 1 hour. Okay? If for whatever reason it doesn't work for you, any last minute question, give that Connect and Excel assignment, which are due at the end of the day today. All right, so upload need to be up for Excel, need to be uploaded on Canvas. You don't need to like hit submit in the Connect, it'll automatically submit it kind of once the due date is pat or once midnight occurs. But I am going to shift that office hour around a little bit. So if you have any last minute questions today, also feel free to send me an email. I can try to kind of give you a response this afternoon as well. Okay. Any questions before we dive into material here? Okay. So we left off last class thinking about finding this union of two events, right? And we said what we can do is we can add the probability of everything that's in circle A and everything that's in circle B. And then we double count what's in the middle of them or what's in the intersection so we can subtract that out once, right? We double count it, subtract it out once means we can only count it one time. So that's fine. We'll kind of see how we could use this with our contingency table. So I think I'll do that first, right? So another way of thinking about this, just before we get to there, after I want to introduce this idea. You can think about breaking the union down into 3 components. So kind of this crescent moon, this crescent moon right, and then kind of the overlap of the two, right? If I broke it down into those 3 components, we'll kind of think about those components. Well, this crescent moon on the left is just everything that's in A, but subtract out the intersection of A and B. So everything that's in A, but subtract out the intersection. You're then thinking about what's this right crescent, what's everything that's in B, but subtract out the intersection. So everything that's in B, subtract out the intersection. We now have these kind of 2 crescent moons. The rest of the union, we got to add in what's in both of them or add in that intersection. Some of these things will cancel, and we get it down to, once again, that the union, right? It simplifies down to that the union is the probability of each event, add together, subtract out, when you double count it, subtract out that intersection. Right? So just another way of thinking about that. So on a contingency table, right? How could I find the probability of A or B? Well, if I know that that union is just the probability of each event added together, and then subtract out what's in both, right? How can I find that from my contingency table? Well, I can't find it directly, but remember, these top four left cells represent intersections of whatever the row and column heading are, and the totals represent the probability bets themselves. The probability of A is 0.6, right? Plus the probability of B, 0.5. Subtract out what's the probability, I'm in A and B, which would be this top cell, which is 0.4, right? And it's just a matter of doing this math. I don't have it. Okay. Any questions on that idea before we keep going here? So, another way of thinking about this. I'll let myself in the room. So I've got circle A, circle B here. Okay. I'm going to break this down into 3 components. Okay. So the first one is going to be this kind of shaded black area, right? How could I write that out? Well, that's everything that's in circle A, but also not in B, right? So it's in A and not in B, which would mean it's in B complement, right? Being not in B is the complement. Okay. I could then use different colors here, try to draw these horizontally. What would this area represent? Well, that's everything that's in circle B and not, right, or outside of circle A, right? So not in A means it's also in A complement. Okay. We then have what's in the middle. Well, the overlap of those two, we already know, hopefully, that's just the intersection. So I've now got these three components. Maybe there's a different way I could find the probability of that union, right? If I could find these three components, add them all up, well, that would be everything that's in either circle. I should have my union. I should get that same value of 0.7. Well, notice I've actually got all three of these things in my table up here. Okay? So a non-technical way, so we get that 0.7. A non-technical way of finding the union, if I go to the intersection of those two banks, create an L, and then add those up, I should actually find the probability union. But that's, that's not very good reasoning as to kind of how to find it. The reason why that works is because essentially by doing that, I've got the three components that I identified up here in the board, right? I've got the probability of A and B complement, the probability of A and B, and the probability of B and A complement. So I've got those three components that I need. If I add these all up, that should give me my union, right? If I add these three components together, I should get my union. Sure enough, what? 0.2 plus 0.4 plus 0.1 gives me that same value of 0.7. So really just two different ways of getting to the same answer, right? You can kind of use the more textbook definition. If it's easier for you to think about, oh yeah, the union is just always add up the probability of each event, subtract out what's in both, right? Or subtract out the intersection. And think about it this way. It makes more sense, to think about, well, I can actually break it down into these three components. I can find those three components, add them up from the table. I get the exact same value. Like I said, the non-technical way, I want to find the union, go to the intersection, make an L, and then add them up. Any questions on this before we move in? Okay. So, one definition I think I introduced last class, I might have mentioned it, was the idea of two events are mutually exclusive. So two events are mutually exclusive means they can't happen at the same time, right? So, if I know that event A has occurred, there's no way event B has occurred. So there's no overlap or there's no intersection. So if two events are mutually exclusive, our life becomes a little easier because now if I'm in the union, I just have to add up the probability of each event. There's nothing in both. There's nothing that I double counted, so I don't have to subtract down anything. Right? Visually, this kind of looks like, two circles that don't overlap on the Venn diagram or in our contingency table. If they are mutually exclusive, we would have to see that the probability intersection doesn't exist, so it should be 0. Right? And we don't obviously see it a lot because not a ton of things that are completely mutually exclusive. We'll start to look at some of these examples, but if they were, we would see it as 0 in that contingency table. Okay. Any questions on this? I think the example I had here, like phone and internet access in the 90s were mutually exclusive, right? If you had one phone line, you couldn't use both at the same time. Okay. So with this idea, that's kind of our first definition, is if they're mutually exclusive, the intersection is 0. We'll talk about a slightly related thing here in a little bit, which is independence, but for now, we'll kind of leave it here. Okay. So we'll revisit this in a little bit later on. So I'm going to give you a better visualization, I think, of this, or I don't know if it's a better visualization, but so for now, take what I'm saying to be true. So let's say everything that's in this white area, it's either in circle A or in circle B. Well, A or B, that's my union. Right? So if I take everything that's in that union and I add to that this blue area, that fills up my entire experimental outcome space. So those two things should add up to 1, right? So if I took the probability of the union, add to that, the intersection of the two complements, that fills up my entire experimental outcome space, that should be 1. So try to give you a little bit of insight as well. Why is this shaded blue area representing the intersection of my complements? Okay. So if I've got circle A here, and I've got circle B here. Okay. Everything that's not an A complement, be kind of where I'm drawing these blue vertical lines, right? That represents A complement. Well, what would represent B complement? Everywhere where there's kind of outside of circle B. So everywhere there are these kind of horizontal green lines, right? So if I think about the space outside of these two circles, notice that's the entire area where I've got this overlap with my green and kind of blue shaded. Well, those green and blue shaded represented the complements of both events. So where they overlap, that's the intersection of the complements. Okay. Now, for the sake of like examples we're working through, like it'll be labeled like this. You won't have to identify that. right? But knowing that everything we've got in the union is what's in those white circles, everything outside of it, that's just representing the intersection of our complements. Okay? We know these add up to 1. So I could then break this down a little bit further, right? I know that the union of 2 events is the probability of those 2 events added together, subtract out what we've double counted, or subtract out the intersection, and then we still have this last piece here, right? So I kind of was just doing some substitution there, right? Substituting in that formula. So now I've just got an equation where I've got 4 unknowns, or right, if I know 3 of them, I can always solve for the 4th, right? So what might that look like? So let's say I had something like this, okay? Where I've got the probability of A, the probability of the intersection of A and B. I don't know the probability of B, and then I've got the intersection of the complements probability as well, right? All we have to do is plug things in and then do a little bit of algebra. So I'm running out of room here, so I'm going to do it up here. But what is the probability of A? 0.5. I don't know the probability of B. The intersection is what? 0.1. And then the intersection of the complements is 0.3, right? Well, now from here, it's just a matter of doing a little bit of algebra, right? So 0.3 plus 0.5 minus 0.1, that's 0.7. So if I subtract 0.7 from both sides, everything cancels. And I've got that the probability of B is equal to 0.3. Okay. So all I'm doing, plugging in my values into this equation, right? If I've got 3 of them, I can always solve for the 4th using a little bit of algebra. Okay. Now, I would suggest always using this formula. Some people are able to visualize this from the Venn diagram. Problem is, a lot of times when people try to visualize it and think through it in their head, they don't use the actual formula. You can like trick yourself because you look at this all 0.5 plus 0.3 and 0.1. So I've got 0.9, so the probability must be 0.1. Well, no, I can't simply just add these values up because when I had the probability of A, that was also kind of including the intersection. So kind of breaking it down into the formula and prevent us from making some kind of easy mistakes there. Okay. Any questions on this before we keep moving? All right, so give you guys a little bit of time. Work on this one. Talk to the people around you. It doesn't have to be dead silent when we're doing this. I want you to talk to people around you, work through the troubleshoot. So let's say I had a very similar setup, right? But now I tell you the probability of A, the probability of B, but I don't tell you the probability of your intersection, right? I still give you the intersection of the complements, right? So knowing these 3 pieces of information, you should be able to solve for the 4th, okay? So I'll give you a couple minutes to work on this, talk to people around you, we'll kind of come together and talk about it. All right, if you haven't gotten an answer in, I'm gonna take your best guess here. It's got what, 25 of us here today, 26. All right, I'm gonna close it out. Make sure you get your answer in. 28, 29. I think I counted 29. All right, so I'm closing it out. We got everybody. So what do I have to do here? Right? first and get rid of this, give myself a little more space. All we're doing is using this exact same formula, right? We just have different kind of values now, right? So what's our probability of A? 0.3. Probability of B, 0.3. We don't know the intersection now, but we do know the intersection of the complements is 0.5. Do a little bit of algebra or kind of add things up here. It's not really algebra. We have this. Now, this is where it can get a little tricky if we're trying to find the intersection. We just have to remember that there's a negative sign in front of it, right? We're subtracting it. So I think if you look at here, really, instead of doing the algebra, I think it's easier to think, well, yeah, what would have to be subtracted for 1.1 to get 1? Well, this would have to be 0.1, right? Now, if we want to do the algebra out, we could add this to both sides, subtract 1 from both sides, and then we would end up with that same kind of result. But I think sometimes when you get to this step, it's even a little bit easier to just kind of visualize, think it through. Okay. Any questions on this? Or anything about what I wrote up here?
What was the point of giving us the 0.5? Did we even use that?
The 0.5 for the probability intersection? Yep. So, right, we've got our 4 components. We get the probability of A, the probability of B, right? Now, if I'd given you the union, you actually could have reversed out and figured out what the intersection is, but I didn't give that to you, right? So you've got the probability of both events. I also gave you the probability of the intersection of the complements, right? So I know that if I take the union, everything that's in these circles, and I add that to everything that's outside of them, or that intersection of the complements, they have to add up to 1, right? So I plugged in those 3 values that I was given, right? 0.3 plus 0.3 plus 0.5, that's where I was getting that 1.1, and then it's just solving for that 4th component. Any other questions on that? Okay with this? So this is one way we can kind of use really like that union law, right? To find these different probabilities. I can get my slides to. There we go. So I've got that kind of everything plugged in here. It looks a little bit different. I kind of did the algebra a little bit different, but the same idea, right? So this is just kind of for reference. If you're going back, you kind of have the answers once I post the complete versions of the slides. Okay. All right. So I'm going to erase this thing. Everybody got it? Okay. So I'm going to jump to this next idea. And let's see if I can do a better job explaining this section. So for now, we have this multiplication, right? I'll try to draw a really extreme case so hopefully you can see how we're getting conditional probabilities. Okay. So let's say I had something like this, right? So we'll start out with kind of a dumb example, but let's say here's my circle A, right? If you were guessing, right, the rectangle represents my entire experimental outcome space, okay? So here the probability of A is what? Relatively small, right? I try to draw it visually to be very small, right? So we can think about all the probabilities we've been talking about up to this point, like the probability of A, the probability of B. These, we'll start calling these unconditional probabilities, right? We're not conditioned, we weren't given any information, right? It's just the underlying probability of A, unconditional. We talked last class, I introduced the idea of the conditional probabilities, or given that something has occurred. So instead, I can think about my conditional probability, and we still say this is the conditional probability of A. We're still looking for the probability of whatever's on the left-hand side of that line. It's just that now we're conditioning on, or given, we have this knowledge that B has occurred, right? So whatever's on the right-hand side of that vertical line, that's what we know has occurred. Whatever's on the left-hand side, that's what we're looking for the probability of. So I kind of use the idea of, slipping and falling outside. That probability is relatively small. But if you tell me, well, actually, yeah, let's say this is the circle B, and B is that it's freezing rain outside. Well, now, once I condition on that B has occurred, it's like, well, my experimental outcome space isn't the entire rectangle anymore. once I know that B has occurred, my new experimental outcome space is just circle B, right? I know I'm somewhere in there. And now, what proportion of circle B is made up of A? Well, now it's a much larger percent, right? So now I'm going to get a probability that A occurs, given or with the knowledge that B has occurred, is now going to be significantly higher than the unconditional probability, right? It makes up a much larger proportion of the remaining experimental outcomes after I have this knowledge. So you can think about really what we're doing there is, okay, what's the new probability of A? I can think about this as, my new experimental outcome space is no longer 1. So if you want to think about it before, like when I had, it's like, okay, what's just the unconditional probability of A? Well, really all that represents is take the probability of A and divide it by 1, the entire experimental outcome space. Now my entire experimental outcome space is no longer 1, but it's just the probability of B, right? Just whatever I've been told is true or conditioned on. Of that remaining space, how much of it is also in A? Well, that would just be wherever their intersection is. Now here I drew it where they're completely overlapped, so that makes it a little bit easier to kind of visualize. But in general, it would just be whatever that intersection is, right? So what's of the remaining space, how much of it is in the, I accidentally erased this. How much of this is in what we're trying to find the probability of, right? Of the remaining space, how much of it is also in A? And then just divide by, well, I've limited the entire experimental outcome space no longer to 1, but whatever I've conditioned on, right? So this is kind of where we come up with how we find conditional probabilities. We could then rearrange it, right? So that I could also find the probability of intersections, right? All I'm doing there is multiplying both sides by the probability of B and kind of rearranging that equation to, just depending on what I know, right? If I know the intersection and the probability of event, well, then this is probably going to be an equation I need to use to find conditional probabilities. Sometimes, I think we'll talk, I don't know if we'll do it Friday, if not, for sure Monday. If instead we're sometimes given conditional probabilities, but we don't know the probability of the intersection, well, then this might be an equation that is a little bit more useful, right? So it just kind of depends on the information that we have, but there's kind of 2 forms of this multiplication rule, okay? So I can do this for either event, right? I kind of did the example up here where I was looking for the conditional probability of A, right? Whatever's on the left-hand side, that's what I'm still looking for the probability of. It's just I've conditioned on this other thing occurring. Here, this first equation would represent the conditional probability of B. I'm looking for the probability of B, but I've conditioned on the fact that A has occurred. So when I'm calculating that, I can think about, okay, now the remaining space is no longer 1, but it's now just the probability of that. Questions on this before we keep moving here? Okay. So here's like a summary of kind of some of the things we talked about. We've got the addition rule, multiplication rule, and then kind of this complement rule. So this just kind of summarizes them all in one place. Let's work through some of this with the contingency table, right? How do we find these conditional probabilities? Because when I told you these top 4 left cells represent intersections, the totals represent the probability of the events themselves, right? So we've got a problem here, which is that I wasn't given a conditional probability. But if I kind of think about the more general form, and I just write it out in the context of my example, I can always find a conditional probability. So what here is what? C1, I don't know, what is it? Given C2? No. R1 given C2. Right. Well, if I think about this is my event A and this is my event B, what I'm going to say is, okay, the remaining space after I've conditioned on C2 occurring, well, my event B is C2, right? It just has a different name, okay? So conditioning on that C2 has occurred, I know my entire experimental outcome space is no longer 1, but just whatever the probability of C2 is. And then of that remaining space, right, how much of it is also in the event that I'm interested in? Well, my A and B are now R1 and C2. So I'm just going to write out the intersection of R1 and C2. Okay. So just taking the general kind of multiplication rule, written it out in the context of my example. From here, what's the probability of the intersection of R1 and C2? Nobody? hopefully we can find intersections. Yeah, so I go, what's the probability of R1 and C2? That's 0.2, right? Those top four left cells represent my intersections. So I've got 0.2. What's just the probability of seeing C2 occur, the thing I've conditioned on? I look at C2, go down to the total, 0.5. And I get that the conditional probability of R1, right? I'm still looking for the probability of R1. I just conditioned on something else occurring, is now 0.4. That is not the same as the unconditional probability of R1, which is 0.6. So having this additional piece of knowledge or information lets me know that, okay, now if I'm still interested in what's the probability that R1 has occurred, there's a much lower probability with this additional information that I now have that I know C2 has occurred, or I know the outcome that occurred is somewhere in the event C2. So you can think about this as before, of the entire experimental outcome space of 1, 0.6 of it was in R1. So the unconditional probability of R1 was just 0.6 out of 1. Once I condition on C2 occurring, I no longer have an experimental outcome space of 1, it's just 0.5, right? So of that remaining space of 0.5, how much of it is also in the event I'm interested in R1? Well, 0.2 out of the 0.5, that's really all we're doing here. We're taking that intersection, dividing by the probability of what we condition on. Okay. Any questions on this idea? And a couple confused looks. All right. So if I follow the general form of this equation, right, and just write it out in the context of my example, it's really just a matter of grabbing some of the information that the contingency table gives me, probability of the intersection, the probability of that themselves, and I can then calculate what these conditional probabilities are. Okay. So what do I want to do here? Under this idea of independence. So we've got this idea of conditional probabilities now, right? Unconditional probabilities and conditional probabilities. We can use this information to then explore something which is independence in events, right? So I mentioned before, mutually exclusive means they can't happen at the same time. Independent means that they can both happen at the same time, but one of them occurring doesn't impact the probability of the other occurring at all, right? So this would be like the idea of what's the probability I slip and fall teaching class today, and then, okay, that's the unconditional probability of me slipping and falling. What's the probability I slip and fall teaching class today, given that it's raining outside? Well, it doesn't matter what's going on outside. I'm talking about slipping and falling here. And so that conditional probability, having this additional piece of information, doesn't really change anything. Right? The other example I'll use later on to describe something is, let's assume the event A I'm interested in is the probability that if I select somebody at random, they're over 6 feet tall. And then event B is that they're a registered Republican. Well, given that they're a registered Republican, now what's the probability they're over 6 feet tall? Those are unrelated, those are independent events, right? Another way to think about this is, if I flip a coin, the probability that comes up heads is 0.5, right? Well, what's the probability then if I flip a coin on the second coin flip? What it's probably comes up heads? Still 0.5, right? It doesn't matter what the outcome of the first coin flip was, the underlying probability is still 0.5, right? So that conditional probability, having this additional piece of information, didn't change the underlying probability of the event that I'm looking at all. So whenever the conditional probability is the same as the unconditional probability, we know that, okay, event B occurring hasn't changed the likelihood that A occurs at all. So they're independent events. Now, if A is independent from B, we can also see, is B independent from A, right? And, they're independent from each other. It doesn't matter which direction we check, right? A is independent from B is the same as saying B is independent from A. Okay? So we can use both of these to kind of check to see if things are independent, okay? A third check I'll introduce now before we go to the contingency tables is if we use that multiplication rule, where we could rewrite, and this is just kind of rearranging this one a little bit, where I can write the intersection of two events by the conditional probability times whatever I'm conditioning on. Well, if they're independent, this conditional probability of B is the same as the unconditional probability of B. Okay? So if we have independent events, finding the intersection becomes a little bit easier, which is just take the probability of each event and multiply it by itself. Right? If this holds, we would know that events are independent. If this equation didn't hold, right, because we know that if they're independent, this would have to be true. So if this equality holds, we know they're independent. If it doesn't hold, we would say they're not independent. Okay. So 3 ways of checking this, right? We can check to see if the conditional and unconditional probability of A are the same, conditional, unconditional probability of B are the same, or to see if the intersection is just the product of the probability of the 2 events. Okay. So we'll see what this looks like using a contingency table. So the first thing that we'll do, since I've got it up here, is how do we check to see if the conditional and unconditional probability of A are the same? Okay. So to check for independence, really what I'm doing is saying, okay, look, is that unconditional probability of A the same as the conditional probability of A? From here, I know that I can rewrite my conditional probability as the intersection of those 2 events divided by whatever I'm conditioning on. Well, now I've got 3 things that I can grab from my contingency table, right? What's the probability of A? Go over to the total, yep, 0.6. Right? What's the probability of the intersection of the 2 events? Go to that top left cell, 0.15. What's the probability of what I conditioned on B? Go down to that total, 0.25. Right? If I take 0.15 divided by 0.25, what I end up figuring out is that's 0.6. And so this equality holds, right? So the unconditional probability of A is the same as the conditional probability of A, being the literal definition of these are independent events. Knowing that B has occurred didn't change the underlying probability of A occurring at all. How did this happen? Well, you can think about it this way. Before, when I wasn't conditioning on anything, the entire space was 1. Of that space, 0.6 of it was an A. So the probability that A occurred was 0.6. Once I condition on B occurring, my experimental outcome space is now only 0.25. And of that remaining space, 0.15 of it is an A, right? And 0.15 out of 0.25 is the same value of 0.6. Okay. So you can kind of think about it like if 2 events are independent like this, like I mentioned, this would be the idea that, the probability that someone's over 6 feet tall. Well, once I've conditioned on that they're a registered Republican, the distribution of height looks pretty similar across the, it looks almost identical between the 2 parties, right? They should be independent, right? I'm sure there's a story you could tell where, I don't know, being a certain height has a certain personality traits. I don't know, but you get the idea that like it should be 2 things that aren't related, right? That knowing the political party affiliation wouldn't influence kind of the height distribution at all that we would see. So we can check it this way, right? And we see that these 2 events are independent. I think that's what I have here, hopefully first. Yeah. We could have also checked to see, is the unconditional probability of B, is that the same as the conditional probability of B? So here, I'm going to rewrite this. So now, if I want the conditional probability of B, it's going to be a little bit different, but like kind of everything just flips, right? I still would want to find the probability of the intersection of those 2 events, right? So B and A or A and B, it doesn't matter which way I write this. Divide by the probability of whatever I'm conditioning on. So here I was conditioning on B. Now I'm conditioning on A. So instead of an experimental outcome space of 1, the remaining space is just whatever is in A. And I can check to see if this holds. Okay. So, oops, sorry. There we go, B. So if I look up here, what's the probability of B? 0.25. What's the probability of the intersection? Well, we had that before, was 0.15. What's the probability of A? Well, that was 0.6. If I put 0.15 divided by 0.6 in my calculator, sure enough, what I figure out is these 2 things are equal, right? That the unconditional and conditional probability of B are exactly the same. So it doesn't matter which way I check it, right? I'll find they're either both ways will tell me that they're independent events, or both ways, if the equality didn't hold, would show me that these are both not independent or dependent events. Okay? So that's 2 of the ways we can check independence. Okay? Any questions on that before you can move in here? Okay, so the first step that we had was we need to figure out how do I find a conditional probability, right? And the idea of independence is I can find that conditional probability. If it's the same as the unconditional probability, I'd say these are independent. Now, I also said that if they're independent, this should hold, right? That the intersection should simply be taking the probability of each event and multiplying it by each other. Right? So we can check that here too, right? Because we have the intersection, 0.15. We have the probability of A, 0.6, and we have the probability of B, 0.25. So it's just a matter of plugging those values in, and what we see, sure enough, 0.25 times 0.6 ends up being the same as 0.15, or probably the intersection. So we can check it any of these three ways. They should all show independent, or they'll all show not independent. Okay. Questions here. I'm going to introduce something that kind of switch gears a little bit. Okay. So I won't make you kind of do the mathematical proof behind why this occurs. So I guess you can kind of take my word for it, or if you have more questions of exactly why, we can go walk through mathematical proof after class if you want to. But when two events are independent, what ends up being true is that their complements are independent as well. Right? So here I could check to see, are the complements independent? Well, all that means is now I'm still looking at the intersection of the two events. I'm looking at the intersection of the complements. And if they are independent, it should be that that intersection is simply the product of the probability of each event. Sure enough, I find the probability of A complement and B complement. So 0.4 times 0.75 is 0.3. And then the intersection of those complements is also 0.3. So there, my complements are independent. I know the events are also independent, or vice versa. Right? So I'll give you a little bit of intuition behind why. So let's say, use my example of what's the probability someone's over 6 feet tall, given, right, that they're registered Republican. Well, those are independent events. So their complements should also be independent. What would the complements be? What's the probability somebody's under 6 feet tall, and given the information that they not are registered Republican, but a registered Democrat? Well, those, being under 6 feet tall and being a registered Democrat, the complements, they're also independent, right? So if we have two events that are independent, their complements will be independent as well. Right? So it's another way we can check it. We don't often do this, but it's just kind of a neat byproduct of events being independent. Any questions on this before we keep moving? We have time. Okay. Excuse me. Let's go through this. This is kind of a stupid example, but I think it makes a good point. So before I do this example, let's think about flipping a coin first, and then we'll kind of graduate to the dice. So if I flip a coin twice in a row, we kind of used this last class. We have 4 possible outcomes, right? I could get 2 heads, right? I could get 2 tails, or I could get a heads and a tails, or a tails and a heads, right? 4 different possible outcomes. So I know the probability, for example, of getting 2 coin flips to be heads in a row is going to be 1 out of 4, or 0.25. Right? But what I could also do is define these events as what's the probability I get the first coin flip to be a head, and the second one comes up heads as well. Right? Those are my 2 events. Right? Well, if they're independent, right, it doesn't matter what outcome I see for the first coin flip. The underlying probability of getting a heads in the second coin flip is still 0.5, right? So these are independent events. So it should be that the intersection is just the probability, and I'm kind of shorthanding this, but of the 2 events multiplied by each other. What's the probability to get a coin flip to come up heads in the first coin, or our first flip? 1/2 times the probability it comes up head in the second, so times 1/2. Sure enough, I get that 1/4, right? Which, if I wrote these out and kind of thought about, okay, this is one of the 4 possible outcomes, I could have figured out that probability was 1/4 or 0.25 as well, right? But I'm just kind of showing this to prove to you that if they're independent, that this will hold, right? So why is that useful, right? Well, what if I want the probability of seeing the first flip come up heads, and the second, and the third? Did I get 3 coin flips in a row to be heads, right? Well, I use the same idea. It's just that now I've got like an added intersection. They're all independent coin flips. So 0.5 times 0.5 times 0.5, right? I don't know if I want to know about 10 in a row, 0.5 times 0.5, 10 times. So basically, if we have independent events, the probability you see a success occur, however many times you're interested in, will just be whatever the underlying probability is. Flipping ahead, so it would be 0.5. And then you would raise that to the power of, and we'll say these are successes, right? Whatever I'm interested in finding here was just seeing heads on a coin flip. Now the constant of dice would do this too, right? If I roll a dice, what's the probability I get a 3? One out of 6 possible outcomes. Well, what's the probability I get a 3 if I throw a dice twice? Well, there, if I get, I need to get 2 specific numbers, 1 and 2, right? The probability of getting each one of those numbers on each roll would be 1/6 and 1/6. They're independent events. When I'm rolling this dice, the first outcome doesn't impact the second outcome at all. And so I would kind of have a similar idea as I did with a coin flip where I can do 1/6 times 1/6. Right. So you can think of, anytime we have independent events, we can always kind of use this fact that the intersection or seeing all those things occurring is just going to be the product of multiplying the probability of each event occurring. Okay. So hope I didn't confuse you too much with this, but this is kind of an interesting thing that we can kind of exploit with independence. I wanted to show you some stuff in Excel. So I have this. Oh, actually, did I put it? I might not have. I know I did it for the other section, and then I just realized I might have forgot to put it in here. Sure did. So let's go. Put it in there. All right. So if you want to pull it up, we're not going to do a whole lot of work in it today. I just want to kind of use it. Set ourselves up for doing a lot of Excel work on Friday. So I have this data set, and I don't know, I had like all the CDC death data. It had it broken down by race, gender. Basically, go to this complete worksheet. I just added all those up and figured out how many people were dying at every single different age, right? So for instance, I found, there's from the data, there's 29,000 people who died within the first year of their life, right? And then there was only 1,900 that died at, when they were age 1, so on and so forth, all the way up to whatever the oldest person that died was. I think it's like 115 or something. So I've got my frequencies, right? That's my kind of first column of data. What I then did is use this sum function, just add those frequencies up. So that should give me the total number of people that died, right? So you can guys see what the oldest person died at 117. And over this time period, there was about 2.5 million or 2.4 million deaths, right? So if I go up to the top here, well, actually, sorry, I'll show you down here so you can see the cell reference. So for instance, what's the probability that I die at the age of 117? If I chose someone at random or someone's life, so what's the probability they die at the age of 117? Well, there's only one person in my data out of 2.4 million. So I take that frequency, simply divide it by the total number of observations, right? This is the same idea as what we were doing when we created relative frequencies, right? So this second column, and I did this for every single age, right? So this column you can really think about, I don't think I had this in there initially, but it's my relative frequency. Or I can convert frequencies into probabilities. The probability I die at the age of 5 is 595 divided by whatever that total amount of deaths I had in my data set was. Right? So I can use this data to turn frequencies into probabilities, and then I could start to answer some of these questions, right? So I might think about something like, I don't know, what's the probability that I die at the age of 70, right? So I can go down here, an equal sign. Let's go down here. So the probability I die at the age of 70 is just that value, right? That's the probability that I'll die at age 70. Well, what if I think about, okay, what's the probability that I die at age 70 given, this is kind of morbid, but given that I make it past the first year of life, right? Because we can kind of see here, within the first year, right, we have an infant mortality rate that's, I wouldn't say it's significant, but it's about 1% of all people that are dying are infants, right? And then as soon as you make it past that first year of life, notice that probability falls dramatically, right? Goes to, instead of what, 1.2%, we're at 0.08%. right? So if I can make it past that first year of life, I know that my likelihood of making it to 70 is going to be a little bit higher, right? Because, it's kind of harder to get past that first year of life. So what I could do is think about, well, here now it's going to be the probability that I make it past the first year of life. So it's the intersection of these two things. So if I make it past my first year of life, I also have to, I know that the probability I make it to 70, really, these are independent events, this hasn't changed, but I can think about taking the intersection of those two events would just be the probability of the event itself. Right? Won't go too deep into this. I'm just kind of using this to show you something here real quick. And then I'm conditioning on making it past the first year of life. So condition, I erased it, but we divide by whatever we're conditioning on. Well, if I can conditioning on making it past the first year of life, actually, sorry, forgot to type this in. All right. The probability I make it past the first year of life would just be 1 minus the probability that I don't make it past the first year of life. So I can use all these rules, right? I'm using the complement rule. I'm also using the multiplication rule here. We start to do, answer interesting questions like this. And you kind of can see, okay, if I make it past that first year of life, my probability of making it to age 70 goes up quite a bit. Right? Or I could play around with if I make it past, the first 3 years of life, what's the probability I die at, whatever age, and we can kind of play around with the different values. But really, what I wanted to use this to kind of point out before we look at a more detailed data set next class is that I can take frequencies and convert them into probabilities by simply dividing by the total number of observations that I calculated those frequencies from. In this case, the total number of deaths. Right? So I've got a couple examples. I'm not sure which one I'll use yet, but you'll see me put up another Excel file. We'll be doing a lot of Excel work in class. I won't use this a whole lot more. I think I'm going to do, and I've got some drug data or some union data. I don't know which one I'm going to use, but we'll have an example where we see, okay, if I can convert frequencies into probabilities, how can we construct our own contingency tables, right? I was just giving you tables with probabilities there. Well, where were those probabilities coming from? So we'll work through a more practical kind of application of working with contingency tables on Friday. So be prepared to do a lot of Excel work. Other than that, I'm going to call it here for today. If you have any questions, like I said, office hours instead of 2 to 4, 2 to 3, and 3 to 5 today. Now I'll try to get an announcement up on campus in between my classes here about that. All right, we'll see you guys on Friday. Yeah.
So when I'm doing the homework and I try to make a histogram, my bins don't bin. Like it'll either come up 1 or 2.
So, yep. So we go back and prep. We're watching this. But I said, when we're doing these histograms, we're not using the built-in what it says is a histogram tool. So you've got your frequencies. So select your labels, hold command and select your frequencies. All you have to do is insert a column or bar chart.
Oh, no, yeah, you were.
And that's your histogram.
Yeah.
Yep. I think you selected too far down.
I know, me too.
Go back.
And I don't counting this tomorrow.
Yeah, so just select the labels here and don't select you only select the frequencies, don't select the name.
I don't use it.
And hold control or maybe select just the labels. Now be able to insert that bar column chart. Should be looking good.
Oh my
And
God.
then you do the same thing with the other units.
Wow.
Yep.
Okay.
Yep.
Thanks.
I might have the same way. And also just want to verify, we're just doing 2020, 2022, right?
No, that was just the full, it was just the full data set, had some stuff we.
Okay, so I did this, but then.
Yeah, so
I
get it.
realized that
See you later. Stay warm.
Yeah, you do. Yeah. Nope, you just got the one, but the problem is you can't use that built-in tool. You'll find notice if you go down. It's not going to give you the right frequency. It's using kind of values that don't match up with the example like that.
And I also didn't know how to copy and paste it, like you're saying in the instructions.
You've got it in there. No, I just meant you can copy those to use as labels. So here, I'll show you the one that we did in class.
You could select all that and just put it in there, but you have to do it one at a time.
So all that I meant when you can copy and paste it over is that you copy, just like you did, copy and pasted the labels.
from there, we're gonna set it up similar to what we did in class, right? Where here's my labels, right? That kind of lets me know where the bin starts and stops. I'm then gonna create two columns that have the minimum and the maximum of each bin. So like this first one goes from 0 to 5,000, 5,000 to 10,000. For your first one, it'd be what? 0 to 125,000, 125 to 150,000. Once you have those two columns set up, it should be pretty quick to kind of set up this count ifs function like we did in the example that we had that was on the tuition worksheet. And once you have used that correctly and you get your frequencies, all you do to get your histogram, you can select your labels, select those frequencies. And we're not using that built-in histogram tool. It kind of, like I said, it kind of messes with it. All we're using is that column or bar chart option. So once we calculate our frequencies, it's just getting them kind of up in a column or bar chart, and that's our histogram.
All right, so I just need to type out all the.
You don't have to type them out. You can type in a few of them. You'll notice like I've got some in the example here. Like we said, well, each one always starts with the last one left off, and they're all of the same length. So I think here I was using bin lengths of 5,000. Here you'll notice after the very first count or first bin, all of them are 25,000 in length.
Okay.
So you can type them in manually, or you can kind of use references
on Canvas as well.
Yep. So this is the one. It says like tobacco youth in class work. Yep.
Appreciate it.
Would that be the frequency or the relative? Or the
You
history?
can use either one.
Okay, so these are relative.
That's fine. Yeah, in practice, I mean, it just depends on what information you want to convey to people, but yeah. Frequency, relative frequency, it's gonna have the exact same shape and everything, so it should be fine.
Okay, I have a question. I know I like emailed you, but how did you get that 25?
So I'm just giving it to you.
Where was that? Because I was so
So
confused.
so on the example we had, right, we have these bin lengths of
Right,
5,000.
yeah. Mhm.
So if I open the Excel homework.
I don't know if I like missed something.
No, I
or
think you're
read
just over,
something
you're
wrong.
overthinking it. So
Okay,
that's just the values I gave you.
right, I got those, but
Yep.
like for the bin length, which was the 25,000.
Yep. So if I look here, notice this one goes from 125 to 150, 150 to 175.
Okay.
It's just I built it into those labels.
Okay.
I chose it to be a nice, easy number.
Okay, gotcha.
The way you were doing
That
it
makes sense.
is we worked through an example somewhere in class where we find the optimal bin length first and then we built it.
Yeah,
Here, we're not doing that because I'm just giving you these specific things.
Okay.
I kind of already did that part for you.
yeah,
Yep.
okay, gotcha.
Yep.
Thank you.
So I just have a question. 14 on the sewer. So.
I mean, someone's, I'm sure I know what it is. Okay, then you can find the variance here.
Yeah, so I
To go up here, so first of all, you want to treat it like it's a sample data. Because it's like 100 prime customers, we know that's not the population. So once you treat it as sample data. You do that right here.
do some of this assignment.
Oh, you did? Okay, so go up here. And then. Hold the one. Hit that a couple times. You'll notice that it's rounding it. I don't know why this is kind of an issue. Like that, it shouldn't have that formatted like that. Okay. So now you try to enter in 0.05. On this. Yep. All right, thank you. Yep, sorry about that.
I just want to know a question. I couldn't figure out how to get these labels, because if once I
Oh, okay.
say what I just do, that's,
So,
yeah.
okay. So click on the number.
Yeah, I like, I couldn't figure out how to actually get the numbers selected.
So what I did there was right click on the numbers, I guess.
Okay.
Whatever this is operating, it's like, you're using the SharePoint version, so
Yeah.
it's kind of a little bit different. You don't have to like use the right click.
All right.
That's we have that.
He did it all the time.
Oh, it's up.
You're in talking first class, right?
Yes. That's very much how you
So
saw
you'll
it.
build data.
Yeah, it's something like that.
Good at.
It's interesting.
Are you an in-person student or online?
No,
Or-
I'm online, so
Okay.
it was just funny to me, because there's like 5 minutes of the first class was, if you're online, you're gonna fail this class.
Yeah.
I was like, okay.
Right,
Is
it's
it
not
anything
bad,
wrong
but his tangent is kind of distracting.
Cyber-
Yeah, I think that's why, although there should.
he keeps marking me off like half points for the homework, so I feel like 9.5 something.
Yeah, I got an 8 on the last one, but originally we graded it as a 6.
Oh, really?
And I sent an email because the homework question asked to compare the new utility
Yeah,
with old prices.
Yeah.
And so the graph was all.
No, I mean,
So I was like,
I know that you're trying to do it, so.
I know that you want to watch the video, so you have to do it.
And he was like,
Um,
yeah, you're right. I remember.
Yeah.
When you upload it,
Oh,
you can add.
I haven't yet. I only.
Oh, there you go.
Only been
Select
through
data.
one of the sheets.
Yeah.
I haven't actually.
So I haven't either.
dedicated time to-
I was out all last week, so I missed on Thursday, but I asked Owen.
Yeah, for some reason, when you're out, when you're working on SharePoint.
Yeah.
like, has
Also,
also-
That makes more sense. Thank you.
Yeah.
Instead of you look up, it's reduced or something number. Okay, so this is a little annoying. Like your labels need to be, so the labels need to be. So you copy and paste.
I don't have, I have time to turn off.
Yeah, there's copy.
I don't have time either. I just talked to, Cecil and was.
There are.
Does anyone say with you at all? Does anyone say with you at all in this class? Do you have any issue with me?
Somebody over here.
Okay, do you have any issue with me coming up at all? Okay, you're the only person I know in the class.
Okay.
You may as well move.
But like, I guess some people. It's super weird, but any other use of the quiz. Followed it.
I say I thought it was funny a few weeks ago, but since I haven't been here.
Yeah.
No, both books are really interesting to me, but I have way too much reading this semester and I have classes from like 12 to 4, so.
Yeah, I just wanted a copy of the book. I wasn't be able to read the Times. That, and I'm not even sure that I even got paid for the last one.
Oh, really?
Yeah,
Shoot. I didn't get paid until like last weekend. So I don't know if it's like a.
well, it's because Kate, brought it up and and mentioned that nobody got paid yet.
Yeah.
And so she made a big deal about it, I guess.
Yeah, I heard some of those book clubs, like, they never process them until like the semester after, so I don't know if it's, they just forget about it or if it's some other issue like that. But I was gonna do the same thing, like if I didn't see it by March or something, I could reach out, but I assume that's what the money was from, it was like 182 or something. Like Ball State payroll, I'm like, I don't work at Ball State, so I hope it's not an accident. It's not too bad. I gotta talk to him a little bit just so I can catch up on some of the stuff I missed. Most of it is just like replicating the graphs from class and then describing, like, you know, that you actually know what you're doing or whatever. What other classes are in the semester?
Let's look. So there's 301, BA 205.
Is that with Lou Vaughn?
You can't, maybe.
Oh, okay. Yeah, I took it.
Of course it was.
And it wasn't a bad class, but it just, none of the homework